Hi, my name is Shahnawaz. In this lecture, we'll study the covariant and contravariant functors. But before discussing these functors, let us first uh, define the faithful, full, and the ammonistic functors. Now, a functor can be injective or surjective when we restrict a functor to home sets. So, when restricting a functor to home sets, we can have, we have the notion of injectivity and the surjectivity. So in such cases, we have the definitions of the faithful and full functors. So let us first define the faithful functor and full functor. So let us suppose A and B be two categories. Be two categories, and say this script f from category A to category B be a functor. Then this script f is called uh, faithful. So we say it is a faithful functor, or respectively we say it is a full functor if uh, if the restriction, so if we restrict this functor to the home status, so if the restriction, so we restrict this f to home sets, so we restrict to home sets from A to A prime, so they are the objects in the category A to home uh, of fa fb. So it takes a morphism f uh, from A to A prime to the morphism f of f from the object fa to fa prime. So if this map is injective, we call it as faithful, and if it is surjective, we call it to be a full functor. So if this is injective and respectively surjective, so in that case we call f, this functor f, a faithful functor or a full functor. So faithful means that the functor has to be the injective functor, and full stands for the functor has to be a surjective functor. Now there is one more definition, I mean the ammonistic functors. So again, let us consider two categories. So let A and B be two categories, and say this script f from category A to category B be a functor. So we call this m, we call this f. So then this f is called ammonistic functor, is called ammonistic. Um, Provided that provided that a morphism f in A, so a morphism f in category A is an identity morphism, is an identity whenever the morphism f of f is an identity. So then we say this script f is the ammonistic functor. So what we uh, wrote here. So suppose we have a category A and the category B, and suppose there is a morphism between the objects A and A prime in category A, and let us call the morphism this little f. Then under the functor f, this setup is mapped to so this A goes to f of A, which is an object in category B. A prime goes to f of A prime, which is an object in the category B. So this morphism little f goes to f of f. So this functor f is called amnestic if uh, I mean if this morphism, if this is an identity morphism on if this is identity whenever this f is identity whenever this is identity. So this would imply that if this is identity, then f has to be identity given that the functor is ammonistic. Now there is a proposition. So let us consider a functor. So let f from category A to category B be a full and a faithful functor. Be a full and faithful functor. That means this f is both injective as well as surjective whenever we restrict this f to home sets. So then for any morphism say G, so we have a morphism G between objects f a and f a prime in the category B. So in B there exists a unique morphism f between the objects A and A prime such that the functor the script f carries this little f to G. Not only that, we also claim that this script f, this functor f, preserves the isomorphisms. So furthermore, furthermore, this script f uh, is an isomorphism. So we say we claim this script f also preserves isomorphism. So this is an isomorphism. Sorry, we say this little f is an isomorphism if and only if G is an isomorphism, which is um, then only if G is an isomorphism. So this is straightforward. The proof of this result is straightforward because the first part is trivial. That follows from the definition because of fullness for a morphism G in category B, we have a morphism um, say little f in category A such that this thing is true. So let us prove this. Since f is full, now full means that this f is surjective when restricted to home sets. So therefore for the morphism for the morphism G between the objects f of A and f of A prime. So these are objects in category B. So there exists say a morphism say H between objects A and A prime such that f of H is G. So this follows from the fact that this f is given to be a full functor. Uh, but uh, f of this little f is also G. So this is also given to be equal to G. But since this f is faithful, now one can note here f of h is G, f of f is G. That means f of h and f of f are same. So by faithfulness, so since f is faithful, f of h equal to f of f implies, so this would imply this h is equal to f. So that means this f is unique. So this proves the first part. Now to prove that this functor f preserves isomorphisms, one should keep in mind, I mean, we know, so actually this says here, I mean, this is the if and only if condition. So we know a functor f always preserve isomorphism. That is, if f is an isomorphism between objects A and A prime, then f of f between objects f of A and f of A prime. So this is also an isomorphism. So this is trivial. Now to prove converse, I mean to prove that if this is isomorphism, then this is isomorphism. So this is what that we need to prove actually. So also note that functors preserve isomorphisms. Functors preserve isomorphisms. So they preserve isomorphism. Therefore, if this little f between objects A and A prime is an isomorphism in the category A, then the then the morphism f of f between the objects f of a and f of b, f of a prime. So this is also an isomorphism. Now, what do we have to prove? Actually, we have to prove if this is isomorphism, then this delta f is also an isomorphism. So conversely, let us suppose G uh, from object f of a and f of a prime. So let us suppose uh, this is an isomorphism. So this is an isomorphism in category B. Let us suppose say f prime be a morphism. Now this is a morphism from a prime to a. So this f is morphism from a to a prime. This is from a prime to a. So be the unique uh, isomorphism such that with a unique isomorphism with f of f prime to be equal to G inverse. So one should note here G inverse is a, so we know by first part of the result. So if we look at G inverse, that is a morphism from f of a prime to f of a. So by the fullness of the functor f, for this morphism G inverse, we have a morphism say f prime from object a to a prime, such that uh, fancy f of f prime is G inverse. So this follows from the first part of the result. So let f prime from a to a be the isomorphism with f prime is equal to G inverse. So this is true. This makes sense because G inverse is a functor. G inverse is a morphism from object f of a prime to f of a, and knowing that this f is a full functor, then we have a morphism from a to a prime to a, and we call that morphism a prime. So this makes sense. So then let us look at the functor f. So f of f prime composite f. So one should note that a functor preserves the composition. So now f preserves no. So this would imply that. So this is equal to f of f prime composed f of f. So that is same as G inverse composite G. Now G is a morphism from f of a to f of a prime. So this will be the identity morphism on f of a, which is same as the f of identity on a. Again, using the fact that f functors preserve identities. So this follows from the definition of functor. This also follows from the definition of functor because functors preserve identities and composition. So we are good so far. but f being faithful, but the functor f being faithful, I mean this is injective, being faithful, so this would imply, uh, now what we got here, so we get this expression equal to this expression. Now using the faithfulness of functor f, we get f prime composite f is actually identity on A. So we have f prime composite f is identity on A. Likewise, we can prove that. So likewise, uh, f composite f prime will be identity on A prime. So this proves that f is an isomorphism. So hence f is an isomorphism. Now let us get back to the covariant and contravariant functors. So we know if we have a category A and a category B, and we have a map F between category A to category B, we call this F a functor, which which maps uh, the arrow F between objects A to objects B to the arrow F of F between objects F of A and F of B, subject to the conditions that this F preserves the identities, i.e., F of identity on A is same as identity on F of A, and F preserves the composition, I mean F of F composite G is same as F of F composite F of G. So we call such functors ordinary functors. So the definition of a functor is actually the definition of a covariant functor, but we skip the term covariant. Now, what do we mean by contravariant functor? Now, contravariant functor is same as covariant functors except this condition. So if we have an arrow from object A to object B, and if this f is a contravariant functor, then this arrow gets reversed. I mean the map, the morphism f of f is from object fb to f of a, given that f is a morphism from a to b. So a contravariant functor reverses in some sense the arrows. So let us define the contravariant functor. So let A and B be categories. A contravariant functor uh, from A to B is a functor, say script f, from the opposite category of A, dual of A to B. So this is what means that this functor reverses the arrows. So in other words, uh, if say we have two objects, say A and A prime, if they are the objects in A and f is an arrow, f is an arrow from A to A prime. then f of f is an arrow from f of a prime to f of a. That is the arrow between a and a prime, which is f. This is carried to the arrow f of f, which is an arrow from f of a prime to f of a. So such a functor is called covariant functor. Sorry, contravariant functor. And an ordinary functor from a to b is sometimes called as a covariant functor from a to b. So one should also mention this here. So an ordinary functor, say from category a to b, is sometimes called a covariant functor. So a covariant functor preserves the arrows. However, a contravariant functor reverses the arrows. Now we have, example of homefunctors. There are two types of homefunctors. Actually, there are three types, but here we discuss two homefunctors. So let us suppose we have a category, say S. So let S be a category, and um, suppose we have a morphism, say F, between objects A and B. So this is an arrow in S. Let us suppose S is any object so let us suppose S is any object in the category S. So we define a function so the function is defined like this. So we are given a category S and an object S in the category and a morphism, an arrow of this category. So using these two things, the object S and the morphism F, we can define a map. So the map is denoted like this. So we have a map which we denote by home of SF. Now this home of SF, we denote this as a function from the home set, the set of all arrows from object S to A to the set of all arrows from the object S to B. So by defining, this carries an element. So suppose we have an arrow, say G here. So this G is carried to the morphism FOG. That is home SF of G is actually FOG. So that means if G is a morphism from S to A, then F composite G is a morphism from S to B. So one can view this from this diagram. So we have an object S here, we have an object A and object B, and an arrow between A and B, which is the map F. Now we say G is mapped to. So first of all, G is an element of home assay, which means G is an arrow from object S to A. So from S to A, we have the arrow G. Now we define this home SF a function which takes the arrow G to an arrow from S to B. So we have to take this G to this arrow. So one natural way to define this arrow is this composite map F composite G. So one can see over here this F composite G is an arrow in home SB, and G is an arrow in G is an arrow from S to A. So this is actually a functor. So we didn't prove yet that that is a functor, but we are going to see this is a functor. So for this is for every G in the home set as A. Now we use this function. So we use this function to define a covariant home functor. So we use this function. Now this function here implies this function to define a covariant home functor. So this home functor is defined like this. So we define this to be home. We keep uh, object S here. So this S is an object of the category fancy S, and we keep a blank here. So this is a functor from the category S to the category set. So as follows. So to define a functor, we have to show why the objects are carried to and why the morphisms are carried to. So we say this home functor, say home S dash, it takes an object A and it maps this object A to home SA. This is a map which takes the object A to the set of all arrows landing in A. So this is actually, so we carry the object A to this set, home of SA. So this is a set, but it's the set of arrows. So an object A is carried to the object of all. This object is actually the set of all arrows landing in A. So one can see over here, this is a set. So this being a set is an object in this set. Now this was the case with objects, and the case of morphisms is like that. So this functor takes a morphism, say F, to home SF, and home SF is this morphism, which is a morphism from home SA to home SB, where where F is a morphism from A to B. So we didn't prove that this is a functor, but we are going to prove that this is functor. So indeed, this home S dash is a functor. Now to prove this is a functor, it suffices to prove that this home S dash preserves the identities and the composition. So this is a functor for any object A, for any object S. So first of all, we have to prove it preserves identities. So home S dash preserves the identities. So let us check what will happen to the identity morphism. So let us evaluate this map to the identity morphism on A. So this goes to the function home S1A. 1A is the identity map on A. So this by definition is a function from the object SA to home SA, because 1A is identity on A is a map from A to A, so it's a morphism from A to A. That is why these two sets they appear to be the same sets. So we have this is a function. So this is for any object A. So this, so one should write here, since home SA is home S dash evaluated on 1A is like this for any object A. So this implies this home S dash takes uh, an arrow, say F, from S to A. So this is an arrow. So if we look at the arrow from S to A, so it is carried to identity on A composite F, which is F. Because if we look at this set home SA, I mean like this home S 1 sub A of F. So this is equal 1 sub A of F, which is F. So it carries F to the object F. So hence, if we look at the identity of, so home S of 1 sub A, I mean this is equal to the identity on home of as A. So that means it preserves the identities. This is the identity on A, and this is the identity on homo as A. Now it remains to prove F preserves composition. Now to prove F preserves the composition, suppose we have two arrows, say from F from A to B, and say G from B to C. Then for any arrow, so actually we have S here, we have A here, B and C. So this is the morphism F, this is the morphism G. So then for any arrow, say phi from S to A, so we have a morphism phi from S to A. Let us look at this map. Home SG, home SG composed with home SF. So this is the composition map operated on the map P. So this is same as home SG home SF of phi. So which is same as home SG. Now this is same as F composite phi. So this is the map F composite phi. And this is same as G composite F composite phi. Which is same as G composite F composite phi. Which is same as home of S G composite F of phi. So that means this composition is same as this thing over here. So that means this function, this home, this is a functor because it preserves the composition as well. Similarly, in the same manner, we can define the contravariant home functor. So this is the definition. So for any object D, the contravariant home functor, which we denote like this. So now we draw, we keep dash at the first place, then the object D. So in the previous case, we wrote dash here, and at the first place we write the object S. Now in this case, we have dash first, then the object. So this is actually a functor from the dual of S to the category set. So this is defined for each object A. So this is defined for each object A by, so we define home dash D of A. So this is the set of all morphisms from A to D. The morphisms landing in D from A. So this is a set, hence an object in the category set. And for any arrow, say f from A to B. Now here the case is like this. So we have object D here, we have object A, object B, and a morphism F. Then uh, home dash D of F is like this, home of F D, which is a map from home AD to home BD. That is erases here. So this is defined by, so it takes an arrow, say, so it takes, so this is defined by, so thus if we have an arrow, say G from B to D, then home of FD of G is actually G composite F. So the situation here is like this. So we have D here, we have A, we have B here. This is a morphism F, and from B to D, we have the morphism G. Sorry, it is like this. Now these two arrows, this G is carried to this morphism. So this is G composite F. So one should keep in mind that this takes the morphism. So this home FD, so this takes a morphism G, which is in home BD, because we have D here, we have B here, we have G here. This is the morphism F, and this is the G composite F. So G is a morphism from B to D. So this means G is an element in home BD. So this G is carried to the element G composite F. So one should see here, this G composite F is actually an element in home AD. So this, that means this functor home dash D. So we can prove this is a functor on similar lines as we did with the covariant case. So but here one should keep in mind that this functor, this reverses the arrows. So that means this is a contravariant functor.